In this DeBacco University video, I'm going to go over the steps it takes to calculate the average atomic mass and go through the step-by-step calculations so you'll be able to make sense of what looks like a mess of numbers here. Soon you'll be able to do these calculations. So before we can calculate the average atomic mass, we have to know what the regular atomic mass is. And that's the mass of a single atom's protons, neutrons, and electrons, even though electrons contribute negligibly. It's measured in atomic mass units. So here we can see protons have one atomic mass unit, neutrons have one atomic mass unit, and electrons are listed as 0. Now they do have a mass, but to put in perspective, it takes over 1,800 electrons to equal the mass of just one proton or one neutron, which is often why they're ignored. Now, if you've looked at the periodic table and seen this atomic mass with a decimal, wonder how that's possible. If protons have a 1 AMU and neutrons have a 1 AMU, how is it possible then to get a decimal? Well, that's because you're looking at the average atomic mass. So what is the average atomic mass? Well, that's a weighted average, not just a regular average, a weighted average of the atomic masses of all naturally occurring isotopes of an element based on their relative abundance in nature. This is the value typically listed on the periodic table. It's also measured in the same unit of atomic mass units. Carbon's average atomic mass is about 12.011 AMUs, and this is because 98.9% is carbon 12, 1.1% is carbon 13, and with trace amounts of carbon 14. So you have to take this weighted average. You're a lot more likely to find a carbon 12 than a carbon 13. This weighted average is what skews this mass unit above that 12 AMU value. This involves isotopes. So what is an isotope? Isotope is a variant of chemical element that has the same number of protons, and thus the same atomic number, and thus the same element, but a different number of neutrons, resulting in different atomic masses. Because we can't change the proton number, because then we'd be changing the element. So by changing the neutron number, that's where we are changing the masses of the same element. So how do you go about calculating this average atomic mass? So the average atomic mass of an element, you take the weighted average, and bolded it here because that's really an important factor, of the atomic masses of its naturally occurring isotopes based on their relative abundances. And this is what causes a weighted average. So if we kind of think about this as related to kind of maybe grades, quizzes might be weighted 20%, exams might be 35%, a term paper 45%. So we could see that term paper has a greater impact on your total grade than just the quizzes at only 20%. We're going to apply that same weighted average concept here to calculating average atomic masses. So our key calculation steps, well, we want to identify the isotopes and their masses. We do this by determining the atomic mass of each isotope in atomic mass units, or AMUs, and the natural abundance, presented as a percentage or decimal fraction. We convert the abundances to decimals, and we'll be going through these steps. If abundances are given in percentages, divide them by 100 to convert them to a decimal form, so we can plug them into our calculator. We multiply and then basically take the sum for each isotope, multiplying its atomic masses by its fractional abundance, and then add those products together. So how does this look in practice? Well, here's our magnesiums, here's our masses, here's our percent abundance. We can see we take those masses, multiply them by the percent converted to a decimal, get our answers, add those three numbers up, and that's just getting our average atomic mass in the end result here. And I don't know why that says K, that should say Mg there for magnesium. But let's go through the steps a little more slowly so you can hopefully follow along a little bit easier. But these are the steps we're going to be going through. So again, just that last thing of that average versus that weighted average, averages versus weighted average. If you had just a regular average, you just take all the numbers up, divide by the total number, and there's your average. So in this example, looking at quiz, homework, test, lab reports, projects, we add them all up since they're all equally weighted, divide by 5, you get 81.6 average. Here's another student that has got the exact same grades, but there's a weighted average. We see very notable, tests are worth 40%, homework's only worth 10%, because unfortunately they didn't do so well on their test. That a greater weighted average, that weights more on the total average, and we could see their average is a 75.7. It's lower than the 81 because they had a 61 average on their test, and that's 40% of the total weighted average. But now let's go and apply this to some elements in the periodic table. So let's calculate our atomic mass for for boron. I'm going to use this as an example. We want to find the natural percent abundance of the mass of each isotope. This information will be provided in some way to you. Keep in mind that the total percent abundances should add up to 100 to count for all possibilities. So here we have boron 10 and boron 11. Boron 10 weighs 10.013 AMUs, boron 11, 11.09, or 11.009, I should say. The percent abundance, boron 10 occurs 19.8% of the time in nature, boron 11, 80.2%. So we can already tell by looking at this 11 is going to have a greater influence. So our number, our final calculated weighted average, is going to be closer to 11 than it is 10 because of the higher percent abundance with this. So let's go through the problems here. Well, we want to convert those percentages to decimals by dividing by 100 and then multiply the masses by the abundance. So this 0.198 and this 0.802 came from, if we flip back for a second, the 19.8% and the 80.2%. Convert those to decimals, we can see this is where those numbers came from. We simply multiply across our row, 10.013 times the percent abundance that's been converted to a decimal. Same thing for boron 11. We get these two numbers here. Now we're not done with those two numbers because we need to take those two numbers and go one more step. With those two numbers, we're now going to add them together and we get 10.81. So we could see that we multiply across here, then add up, and this is how we're getting our weighted average here. Another example here, we're looking at the average atomic mass for iron. Here's our isotopes, here's our mass, and I give a percent abundance with a question mark, and I also a mass with a question mark. Well, if we look at the mass here, iron 54 is a mass of 54. Iron 56 is a mass of 56. So iron 57, you can probably fill that one in. And then our abundance, well, how do we calculate the abundance? Well, we know that if these are all the given isotopes, they have to add up to 100. So if we take all the numbers given and subtract from 100, we'll get the total percent abundance. If we do our math correctly, we should get iron 57 being 57, and our percent abundance should be 5.08. So now when we add all these together, now we get 100% in total. So just a little way to kind of be able, if I give you a missing portion, I hopefully give you enough information you can calculate and fill in those missing parts. Now that we have all our data points, we filled in all the gaps, now let's go to the next step. We're going to convert our percentages to decimals. Now this is very important here. So as we look through here, we got our numbers. Now we're going to convert those percentages to decimals. So how do we go about that? Well, we move the decimal point 2 spaces to the left. And I say be careful. And I spelled careful wrong because you want to be extra careful with this. So when we're looking at this, why do we have to be careful? What messes a lot of students up is this 0.28. They think that's a decimal already. That's a percentage. We still have to move that 2 places to the left. So 0.28 becomes 0.0028. So don't get tripped up on those small percentages. Still convert them to decimal form. Now multiply the mass by the abundance. We did the same thing we saw in the previous example. Take the mass, multiply by the abundance, get a number. Take the mass, multiply the abundance, get a number. Take all of these numbers now, and we're going to add them together. And that'll give us our final weighted average atomic mass for iron, which is 55.9116. If you were to look that up on the periodic table, you probably will see something very, very close to that. It may not be exact. Some periodic tables use slightly different precision in their weighted averages, but it should be very close to that if you follow this procedure, and hopefully you're able to calculate that same exact number for the example provided here.